Easy steps towards the virtual prototyping using the SystemVerilog DPI. Abstract. The hardware and software worlds have been drifting apart ever since John W. Tukey coined the term software and bit back in 1958. Tukey introduced these terms as computers were evolving from the electromechanical to electronic components. Hardware has long meant something you can touch and typically assemble from parts into a larger system. Software has come to mean that which you can touch, yet that which you can change without touching the hardware. In the early age of the software development, programmers required extensive knowledge of proprietary hardware architectures in order to write a program that executed on them. Today, software programming has evolved to standardized languages like C or C++ and Java. Also, programmers can write code independent of the hardware architecture the programs are learning on. Finding engineers experience in both the disciplines is becoming very difficult, making communication between software and hardware engineers daunting to say the least. This is further complicated because of different modeling languages used by each discipline and the different abstraction level required during each phase of a project. The virtual prototyping is an evolving methodology for verification of the software and hardware in a single environment that is designed to catch these communication breakdowns. Performance of each virtual prototype is critical to the successful completion of this verification task. Execution of software on simulated hardware models can be many order of the magnitude slower than a software executing on the real target hardware. So virtual prototyping methodology partitions the execution of software and hardware into the proper abstraction level to achieve the desired performance versus accuracy trade-off. This paper discusses various virtual prototyping methodologies available along with the verification and performance goals each is optimized to address. It explains the trade-off considering different perspectives that hardware and software engineers are able to understand. In particular, this paper will demonstrate a virtual prototype using a modern interface provided by the SystemVerilog DPI-C contract that bridges the C software world with the Verilog hardware description language HDR world. Additionally, this paper will explain mechanism for a transaction-level communication between the hardware and software using a UVM testbench. It will demonstrate software transactions on the C side that are converted into sequences of cycles represented by the call to the UVM register abstraction layer. RAL. This makes the hardware verification environment considerably reusable with the virtual platform environment. Chapter 1 is introduction. By definition, a system-on-chip (SoC) device is the blending of software and hardware domains. The architecture of a SoC is a compromise of the trade-offs between the implementation of tasks in hardware or software based on a number of performance goals. Verification of SoC is usually divided independently into their respective domains before full system-level verification begins on the actual platform or a representative prototype such as a hardware FPGA or emulation system implementation. Unfortunately, the availability of a full system usually comes too late in the project cycle to get the desired amount of verification completed in time. So the virtual prototyping is a methodology that addresses this problem by getting earlier access to a full system using a variety of software emulation and simulation techniques. If you look at the typical component that make up an SoC, you may see what is shown in Figure 1. Figure 1 is typical SoC block diagram. It's an embedded processing unit or units and each subsystem for executing instruction, the core. A bus or fabric that connects all the processing unit and device together, AHB and APB as in this example. A set of instructions in a software firmware that manage the entire SoC, executing each processing unit represented by DUB data and the RAM or ROM. A set of hardware devices that communicate through the standard protocol interfaces with devices external to the SoC. A set of hardware devices that manipulate data external to the processing unit, other master or slave bus devices, a DMA controller as in this example. In most cases, the processing units as well as some of the hardware devices acquired intellectual property (IP) and are considered pre-verified by the organization that developed them. So some of this software is also acquired, such as the embedded OS and drivers that go along with the acquirement hardware devices. That leaves the critical task of verifying the application software, the application hardware, and all the communication mechanisms that connect the SoC together. Chapter 2 is verification architecture. The methodologies for verifying hardware and software separately are fairly well understood. Each methodology has a set of practice that requires some intimate knowledge of their respective domain. Since an SoC uses a fairly standard protocol for communication across the system, it is relatively easy to verify each individual component in isolation. However, the task of verifying the communication between those domains becomes a struggle without having the complete platform available. A virtual prototype addresses a portion of this problem by providing high-performance models for the missing hardware components. The software component may be cross-compiled into the same host processor running the virtual prototype, which is typically referred to as native code, or there may be a software emulation of the target processor running on the host. On the actual platform, an embedded processor communicates with the other component of SoC using address-mapped memory references. Taking advantage of standard protocol, a virtual prototype represents the communication between components in terms of application-specific procedural interface (API). The memory references generated by the embedded processor need to be converted into API calls in a simpler prototype or intercepted by the virtual prototyping system and routed by a software backplane in Figure 2 to call the appropriate software models. Figure 2. Virtual prototype backplane. The virtual prototype achieves higher performance by having a host processor running nearly as fast as the target processor, and a bus cycles abstracted into simple transactional-focused core, function calls, and performance of a virtual platform may be within one or two orders of magnitude of the actual system, which may be enough to run the full embedded OS. Understandably, introducing hardware-level description models into this virtual platform will have a tremendous impact on performance, limiting simulations to a smaller portion of the OS and stripped-down segments of code. Verification of hardware can usually begin for each component individually without waiting for a significant amount of the system to be in place. One or more components can be connected to a physical bus for a subsystem simulation. Traffic on each bus may be generated by drivers provided via verification IP, VIP in place of the actual target processors. Figure 3. Block level verification environment. Performance of this hardware verification environment is reasonable because the processor has been replaced by a simplified bus functional equivalent and only the necessary hardware is in place. There is no need to verify the complete hardware design as a full system if certain components have been verified individually, such as the processor itself. Ideally, only the communication between components need to be verified at the hardware level. So correspondingly, there is no need to verify the hardware by running software on the processor. Doing so would be prohibitive in terms of performance because of the extreme number of redundant software bus cycles. The only remaining need to verify that the software can properly access the hardware components. Traditionally, the most efficient way of executing software that accesses hardware models has been drive the physical bus with a high-level processor model, like an instruction set simulator (ISS). However, the ISS model is burdened with the task of driving bus signals with pin level or cycle level accuracy. So we can combine the most efficient methodologies from the virtual platform environment with the most efficient two methodologies from the hardware verification environment. We can achieve our desired performance target. Figure 4 is mixed software and hardware simulation. So the SystemVerilog Direct Programming Interface DPI was designed to integrate the C language with a hardware description language at the software level of procedural calls. In contrast, the programming language interface PLI was designed for pin level transaction and other tool interfaces. The DPI link allows us to keep the communication between the virtual bus handler and the bus agent at the software abstraction level of procedural call transactions. The fact that a virtual platform can be run at one level of abstraction while the hardware environment is using another level of abstraction has a significant impact on performance as well. Chapter 3. Modeling abstraction levels. The choice of abstraction levels is very dependent on the particular application, so the key point to remember is that the goal of creating this mixed verification platform is to verify communication between the software and hardware, not all the software and hardware in total. In the simplest terms, levels of the abstraction are characterized by timing accuracy. The OSCI System C TLM 2.0 standard introduced terminology for coding styles that we can refer to here. UT, untimed, limited or unspecified timing accuracy. At this level, only ordering of operations matters that are there, and there may be no bookkeeping of elapsed simulation time. So usually timed LT. Time is broken into slices or some quantum unit. An SOC virtual platform is likely to choose the execution of an instruction as its quantum time unit. Approximately timed at 80. Quantum units are broken down into phases unless the tracking of an elapsed simulated time is enough to gather the relative performance statistics. Cycle accurate and cycle callable CC timing is the accurate enough to the run in lockstep to match the time models at the pin level, clock, or bus cycle boundaries. So on the software side, any one of these abstraction levels may be attained when you cross-compile code written in your target processor to run natively on your current host. You may not care about timing, only the functionality of the code. There might not even be a way to represent the target processor's timing. If you compile your code to run an ISS model on your target processor, the model may have a statistics for instruction execution times for each instruction and simply provide a summation of results that will be usually timed. To model the effect of a predefined system may require that you use an approximately timed model. The hardware modeling side has fewer choices. Most synthesizer designs require a cycle accurate or lower level abstraction than what has been described here. However, the test bench verification modeling can be at a much higher level. Methodologies such as UVM let you treat the verification architecture more like software. The UVM's register abstraction layer, while is designed so that you can write hardware verification tests by providing memory address maps that they either generate or intercept memory references from simple procedures calls written in your test bench. So, chapter 4 is synchronization between abstraction levels. At the simplest level, let us think of our software as native C or C++ code running on the host processor, where our host processor is also where the simulation of hardware and SystemVerilog is running. We can use the SystemVerilog DPI to blend the two languages to having the software call a function that represents a bus transaction. In more sophisticated virtual prototype system, memory references are intercepted and routed by the table to the appropriate handler, but the end result is the same. A memory reference becomes a procedural call. The key features of a SystemVerilog DPI is that it lets a SystemVerilog function or a task appear as a simple routine on the C side, and a C routine appears as a task or function on the SystemVerilog side. A subset of compatible argument types may be accessed transparently without any knowledge of the language used to call the routine. Compatible types are those with the same semantic meaning and representation in memory without any need of conversation. Figure 5 is software to hardware DPI link. So in the code fragmentation shown in figure 5, the C code has no notion of timing exception when it calls the DPI exported tasks, which are both cycle accurate on SystemVerilog side. The C routine calls and is blocked until the APB read and the APB write tasks have completed. While the C code is blocked, simulated hardware times advances on the SystemVerilog side waiting for each clock cycle. There is explained further in figure 11, interprocess communication. Figure 6, compressed hardware simulation timing. In simulation shown in figure 6, hardware simulation time only advances during the bus cycles chosen by the virtual prototype to model and hardware. There may be thousands of consecutive either hardware bus cycles between the active bus cycles. The hardware design might require additional simulation time during either bus cycles to execute the activity accurately. The virtual prototype may also have its own concept of time by counting the number of instructions executed. We can provide an idle task the advances time to gain some extra level of timing accuracy that represents some percentage of idle bus activity. For optimal performance, there is no need to account for every idle bus cycle. So that there is the figure 7 approximated hardware simulation timing. Now, instead of injection a separate idle bus operation, you could add the instruction count on to each bus operation and have the SystemVerilog inject some constrained random number of bus cycles. Some designs have interrupted to need to account for the idle task as well as any bus cycle tasks may be modified to report back an interrupt was requested. Figure 8, interrupt monitor. A completion model between the hardware and software prototypes need to be agreed upon. Depending on the application, the hardware side can either just report that the interrupt was requested during the bus operation just to complete it, or abort the operation and return immediately stating the operation was incomplete. Chapter 5, Flows of Transaction. For easier maintenance and reusability, define a standard transaction instead of creating individual routines and various numbers of argument lists. A transaction is simply a structure of data that represent a common set of arguments that are typically passed to the model method. They can be packed or unpacked into a single array of bytes, making data transfers across the inter-language boundary much simpler. The design of a transaction is shown in Figure 9. Figure 9, the transaction specification. Depending on the operation, only some of these fields may be populated at the start of the transaction, others will be filled in at the time of completion. An important consideration in mixed language environment is that each side of the language boundary is responsible for allocation the management of the memory used by a transaction. In the earlier example, we just passed a compatible data type, like an int, as an argument that was copied as the call was made. This is fine as long as the size of the argument is known fixed size of both languages. Passing a pointer to a block of memory unknown size is allowed. Memory for transactions with dynamic sizes must be allocated both sides before making the call. Some methods for dealing with this issue are: allocate a fixed maximum size for your transaction and use the length field to trim the payload. Send the payload in fixed size blocks over multiple operations, so if your block size was 2K and you need to send a 5K payload, you would need to send a payload over the 3 transactions. Split the transaction into 2 calls. The first call would specify the length of a payload to allocate, and the second call would use the allocated state from the first call. So, Chapter 6. The need to be the master. So far, we have not considered how to get the communication between the virtual prototype and the hardware simulation started. Software running on a processor runs in a limited number of threads, whereas the hardware is by its nature represented by a prolific number of threads. In practice, hardware simulators do not represent the thread the same way the software does, so there will need to be some kind of mapping. Going back to the simplest environment where the software is just C code natively compiled or simulation hosted and hardware. The C code can be started from the SystemVerilog side by calling a DPI-C routine that has been imported as a task. In this case, the SystemVerilog side is a master thread. In the following example, the routine C code has been imported as a task as opposed to a function which follows consume time. The way C code consume time is calling an exported task V code. The figure 10 is starting a C thread. However, more realistic virtual prototype systems wanna be the master starting their own thread and just having the API calls act as a slave to their thread. And the most common way to make this happen is to use the interprocess communication socket IPC, and an IPC socket is a more host OS mechanism of message passing. A server thread sends a message to a client and receives responses from a client thread. Both threads can be started independently of each other as a master thread, but will block waiting to receive the message or response. The only significant difference between the master and the slave is the master process initiated the socket and slave the processor connected the socket. After the negotiation, the virtual negotiation. That negotiation, the two processes can be completely independent of each other, using the IPC messages to synchronize with each other. The figure 11, inter-process communication. The two loops in figure 11, represent two independent processes. The software virtual prototype may have been main processes, one of which is the virtual backplane intercepts and calls the software bus model. The software model sends an IPC message to the C thread started by the hardware simulation client and waits for a responsive message. The C thread is the other process waiting to receive an IPC message, and then they executed the transaction by calling the SystemVerilog functional models exported through the DPI. Chapter 7, Integration with the UVM. The use of the existing test bench from the hardware-only based verification environment is always encouraged. The sequence mechanism and the UVM provide a convenient mechanism to convert the bus transaction into a ready set of a pin wiggled to the duty for any particular hardware protocol. The SystemVerilog DPI enables the C code to start sequences to send the transaction through the test bench that eventually reaches the interface to the duty. The UVM's register package provides an additional layer that directed the appropriate memory addresses to the appropriate interface use a register map. Figure 12. UVM test bench reuse. In the environment shown above, the UVM sequences are generated by either a pure UVM test, the virtual prototype process, or a combination of both. The Chapter 8, Summary. The techniques shown in this paper has been deployed on several projects where the virtual prototype have been modeled in a variety of environments from an internally developed platform, open source Python-based stimulus generator, and a commercially available system such as Wind River Symix. There are a number of other issues that time did not permit going into detail in this paper, but have been addressed in some of these projects. These issues including dealing with the multiple interface thread and controlling the interactive debugging environment of two processes communicating through IPC sockets. Okay, there are all the 8 references. Okay. Today, I read this paper together, the easy steps toward virtual prototype using SystemVerilog DPI from DVCON2013. Thank you for your time. See you next time.